Hello everyone, my name is Xiangyang Wang from the College of Computer Science, National University of Defense Technology, China. Today I will present our work titled Robust Volumetric Wave Rendering for Aerial Spatial Audio in Dynamic Media via Cumulant LBM. This work focuses on urban acoustic rendering in dynamic media. Our goal is to turn a numerically robust LBM solver into a practical acoustic baking pipeline for aerial spatial audio and city-scale scenes. This slide shows the structure of my talk. I will first introduce the background and explain why dynamic media make outdoor spatial audio more challenging. Then I will discuss why standard acoustic solvers may fail under strong convection, shear flow, and voxelized urban geometry. After that, I will introduce the core idea of VLLBM and its graphics-oriented acoustic baking pipeline. Finally, I will present the hierarchical validation results and the city-scale experiments, showing the physical credibility, numerical robustness, and graphics relevance of our method. Let us start with the motivation for outdoor spatial audio. Low frequency diffraction, interference, and multipath propagation cannot be ignored. These wave effects directly affect auditory perception and scene realism. At the same time, real urban environments are not static or homogeneous. Local winds, street canyon flows, and shear layers can change sound propagation paths, arrival times, and energy distributions. Therefore, we need more than a local acoustic solver. We need a flow-aware, full-wave acoustic baking framework that can generate reusable acoustic data in city-scale, voxelized scenes. The difficulty in dynamic media can be understood at three levels. First, geometric acoustics is efficient, but it cannot explicitly resolve low-frequency diffraction and interference. Second, many standard wave-based solvers become numerically fragile under strong convection or non-uniform shear. They may suffer from dispersion, loss of stability, or even complete breakdown. Third, when these dynamic media effects interact with voxelized building boundaries, boundary-induced artifacts, and high-order numerical errors can be further amplified. Therefore, our practical, urban, acoustic rendering framework must remain stable when wave propagation, background flow, and complex, voxelized geometry interact. This slide gives an overview of the VLLBM framework. The framework can be divided into 4 connected modules. On the left, we have input and media preparation, including urban CAD or GIS, assets, voxelization, and prescribed background wind fields. In the middle, the VLLBM solver core performs the third quarter of 27 Cumulant acoustic simulation on a Cartesian lattice. The upper right part shows the validation suite, ranging from static propagation and boundary scattering to dynamic media stress tests. The lower right part shows the flow-aware outputs, including volumetric wave fields, receiver-side temporal responses, and baked acoustic data for downstream spatial audio queries. So the main point is not just to introduce an LBM collision model. Instead, we build a complete acoustic baking pipeline for rendering applications. The core idea lies in changing both the collision space and the reference frame. Traditional BGK or TRT models usually relax distribution functions in a static reference frame. In contrast, VLLBM first maps the state into central moments or cumulants, and then performs mode-wise relaxation in a local co-moving frame. The intuition is that low-order acoustic modes, which carry the physical sound waves, should be preserved as much as possible. At the same time, high-order, non-physical modes, which tend to grow near shear layers and voxelized boundaries, should be strongly damped. In this sense, cumulant relaxation acts as a selective numerical stabilization mechanism, making the solver more robust in dynamic media. This slide explains why the framework is graphics-oriented. Our goal is not only to obtain a one-time simulation state. Instead, we aim to generate acoustic assets that can be reused by later rendering stages. These assets include voxelized scene data, dense volumetric wavefields, receiver-side temporal responses, and reusable baked acoustic data. This follows a common pattern in graphics. Expensive physical computation is performed offline, while runtime or downstream systems can query the pre-computed data more efficiently. Therefore, the method is designed not only around numerical correctness, but also around reusability and application facing acoustic data generation. Here we show a key design for dynamic media acoustic baking. The two-pass strategy in the paper does not simply split source propagation and receiver extraction. Instead, the first pass is a source off-base flow simulation. It builds a background reference state that already includes the effect of urban geometry. The second pass is a source on acoustic simulation. The acoustic source is emitted into the dynamic medium, and the wave field evolves under the background flow. Finally, we subtract the base state from the source on result to extract weak acoustic perturbations. This design is important because the acoustic perturbation is on the order of 10 circumflex 6, while the aerodynamic background can be on the order of 10 circumflex 2. The two-pass strategy makes the flow-aware acoustic response measurable and analyzable at city scale. We now move to hierarchical validation. The first test is static medium propagation. The purpose of this experiment is not to show that 27 cumulant is always better than all baselines in static media. Instead, it verifies that the cumulant formulation does not sacrifice baseline acoustic fidelity in the most fundamental wave propagation setting. From the centerline profiles and error metrics, we can see that 27 cumulant preserves the correct phase propagation and the main waveform structure. It remains in the low error group, comparable to the strong 19 TRT baseline. This is an important prerequisite for the later dynamic media tests. The robustness improvement is not obtained at the cost of static medium accuracy. The second validation case focuses on rigid boundary scattering and low-frequency diffraction. This is important for graphics and spatial audio because urban environments contain many occlusions, corners, and street canyons. Sound waves must not only propagate, but also correctly represent reflection, scattering, and diffraction into shadow regions. The SPL directivity plot on the left shows the multi-lobe structure around the shadow zone. The instantaneous wave field on the right shows the diffraction fringes behind the cylinder. The main message is that before entering dynamic media cases, 27 Cumulant remains competitive with 19 TRT in boundary scattering, fidelity, and stability. This slide serves as a transition from static media to dynamic media. we consider a moderate shear flow to examine how different collision models behave in a non-uniform background flow. The one-dimensional profiles on the left show that at this level of shear, 19 TRT and 27 Cumulant remain macroscopically aligned. The two-dimensional fields on the right reveal some fine-scale structural differences near the shear layer. More importantly, the BGK variants already start to show visible distortion. This indicates that as the background flow becomes more complex, the robustness of the collision model becomes a key factor for wave field credibility. This slide presents the stress tests, where the difference between the methods becomes much clearer. We further move into high subsonic shear flow and strong crosswind with high-frequency excitation. Under these more demanding dynamic media conditions, 19 TRT becomes unstable or produces corrupted wave fields. In contrast, 27 Cumulant still maintains bounded one-dimensional profiles and coherent two-dimensional wave structures. So the comparison is no longer about small quality differences. It becomes a question of whether the solver can continue to operate under extreme dynamic media conditions. This directly reflects the core problem targeted by VLLBM, maintaining stable and interpretable wave fields under strong convection, strong shear, and high-frequency excitation. After the controlled validation experiments, we scaled the method to a real city-scale scene. This slide summarizes the scale and computational cost. The full urban domain contains about 140 million voxels, including about 115 million active fluid voxels. The simulation uses 20 nodes and 600 NPI tasks. For static city baking, we simulate 2.0 seconds of physical time with a wall clock time of about 30.6 minutes. For the dynamic wind subdomain, we use about 12.5 million active voxels and simulate 16.6 seconds of physical time with a wall clock time of about 13.1 minutes. The key point is that VLLBM is not limited to small canonical examples. It can be scaled to city-scale acoustic baking with explicit reporting of parallel resources and computational cost. This slide shows the city-scale static baking result under quiescent conditions. In the rendered field, we can observe multipath scattering in street canyons, no line of sight, diffraction, recovery behind occlusions, and softened acoustic shadows. These are wave effects that geometric acoustics tends to simplify or miss, especially in low-frequency and strongly occluded environments. Therefore, the value of city-scale full-wave baking is not just to produce a visually richer wave field image. More importantly, it provides a physical data foundation for downstream spatial audio, including diffraction, interference, and multipath effects. This slide shows the wind-aware receiver response under a tailwind condition. The curves on the left show the temporal response at the receiver, while the field visualization on the right shows the city-scale propagation structure. Two numbers are especially important. First, the arrival time shifts from 0.588 seconds in the quiescent case to 0.5 seconds under the tailwind condition. This reflects the convective Doppler shift. Second, under the coupling between the urban canyon and the 60 meter per second tailwind, the peak pressure is amplified by about 27 times. This shows that wind does not only change propagation speed, it can also significantly reorganize local energy distribution and receiver-side acoustic response. This slide summarizes the evidence at 3 levels. The first level is wave physics. The framework explicitly shows physical effects that are perceptually relevant for spatial audio, such as diffraction, interference, and convective Doppler shift. The second level is robustness. Beyond moderate cases, the stress tests reveal the stability limits of different collision models under strong dynamic media. The third level is scale. The city-scale experiments show that the method can generate reusable volumetric acoustic data rather than only isolated examples or qualitative images. Therefore, the contribution is supported by physics, robustness, and scale at the same time. From the perspective of graphics and rendering, the key takeaways can be summarized in 3 points. First, LBM provides stronger robustness. It can maintain stable wave fields under dynamic media conditions, such as shear flow and crosswind. Second, it has clear rendering relevance. Its outputs are designed for flow-aware spatial audio baking. Third, it has data value. It can provide physically grounded data priors for neural acoustic fields and hybrid acoustic representations. Therefore, we view LBM as an acoustic engine for graphics applications rather than only a CFD-style solver upgrade. To conclude, LBM turns the third quarter of 27 Cumulant LBM into a rendering-oriented acoustic baking engine for dynamic media. Through static propagation and boundary scattering experiments, we verify that it does not sacrifice baseline acoustic fidelity. Through moderate shear, high subsonic shear, and crosswind stress tests, we demonstrate its robustness advantage in dynamic media. Through the 140 million voxel city scale experiment, we further show its potential for urban spatial audio data generation. In future work, we plan to explore AMR, CPU-GPU heterogeneous acceleration, more complex urban wind scenarios, and downstream neural acoustic field representations. This concludes my presentation. Thank you very much for watching and listening. I would also like to thank the EGSR organizers and the reviewers for their valuable comments and help. Thank you.
Rather obvious question that I thought about was like, do you think this could be applied to other domains instead of acoustic, like for example, propagating electromagnetic radiation? Of course, the scale, depending on what you do, radio or Wi-Fi or visible light, matters a lot. But what do you think it's, would you have to change from your method to support those domains?
Thank you a lot for a simple question. And I think it's our core method does not need a full redesign to support electromagnetic wave propagation. Only target party architecture are necessary. In our field work, we actually plan to test coordinate wave simulation as one of our follow-up research dissection. Thank you.
Okay. Thanks. Any more questions from the audience? So in the interest of time, let's thank the speaker again and move to the next talk. Thank you.
Thank you.